So here's our next problem. This is basically an application of Burnside Lemma. It pretty much mimics the previous problem. So how many essentially different coloring patterns on an 8x8 chessboard by using only two colors, black and white. You can generalize quite easily. You can change these two colors into C colors, different number of colors. The general result won't change. So let's remember the group actions. So again, on the square, so these are our group members: E, A, B, C, P, Q, R, and S. So recall that A is pi over 2 rotation, B is pi rotation, C is 3 pi over 2, P is a reflection across the horizontal, Q is a reflection across the vertical, R is the diagonal, S is the other diagonal rotation, and E is just do nothing. Let's focus on A first. So we need to find the fix of A. How many elements are fixed by A, right? So, well, obviously the fix by E is the whole thing. So, well, let me start with E then. Okay, so how many colorings are fixed by applying the identity element? It's all of it. How many is all? Because this is an 8x8 chessboard, so we have 64 little squares here, so therefore each one have two different ways we can color. So 2 to the 64 is, so all these 2 to the 64 different patterns, colorings are fixed under the group member E. So now the more harder case, fix of A, rotation by 90 degrees. If we can figure out what's going on here, pretty much the rest is obvious. So what do we do here? So we want to rotate this coloring by 90 degrees, and as a result we wonder, let's say clockwise, and then as a result we wonder how many colorings are essentially the same. So let's focus on some elements here. So focus on the element in this square here. So obviously this must be the same as this element, right? Because after rotation, so this element will be carried, the top left element will be carried to the top right, and then the top right then will be moved over to the bottom right, and the bottom right will be moved over to the bottom left, and the bottom left will be moved over. So all these should be the same color. So only colorings which have these four squares the same color will be inside the fix of A. And the same thing for, let's say, this cell here. Whatever this color here is the same in this one, the same in here, and the same in here. So you can, in a similar way, the same here, here. So all these should be the same color. And you can keep doing this, like, I don't know, let's say this one. So after the rotation, that would be probably, I think it will go this way here. And then it will go probably here, I guess. And then here. So all these four should be the same. Do you see what's going on in here? So the best way to understand this is to think of it in terms of, yes, you've known it, in terms of cycles. Yes, so we need to count how many cycles there are. Yeah, there's a cycle notation for groups. For this particular case, notice that this element creates a unique cycle here. So it goes here, comes here, comes here, comes here. So that's a unique cycle. So every element in that cycle should have the same color. So basically it's a matter of counting how many cycles there are. So that's one cycle. Then we have another cycle of these red ones. So obviously, so you can see there's another cycle here. So the question is, how many cycles? Well, it's actually not too hard once you realize the following thing. You just need to figure out how many in this portion of the 8x8 board. So basically on this 4x4 board, the number of different colorings available here will just determine the rest of the colorings in the rest of the board. So you identify this the number of colorings in this 4x4 portion of the chessboard. the whole chessboard coloring is defined. So therefore the fix of A would be 2 to the power 16. There are actually 16 cycles. And so, and it turns out that fix of A is basically the same as the fix of C. Fix of B is slightly different. The fix of B, the 180 degrees, so we need to be cautious on that one. So obviously the top left will be mapped onto the bottom right, and so that's one cycle there, and then the bottom right will be back on top left. So as I said, that's one cycle, and the top right and bottom left are paired, so that would give you another cycle. So yeah, so each one will have 2. So as a result, what we can do is we can split the 8x8 board from the middle. It's from the middle section. I don't know if you guys can see it, so let me just make it a different color. So different number. So once we fix those colorings here on the top portion, the bottom portion is automatically defined. So therefore, so we have 2 to the power 32 different ways to color the top portion, and so that would be it. So all we are left with are the reflections. So based on these ideas, it's not too difficult to figure out that we can continue the same way, I guess. The fix of P, recall, was the horizontal, so therefore the fix of P would be we have 32 members above the horizontal, so therefore the number of elements here would be just 2 to the power 32, and that number is actually equal to the fix of Q as well. In a similar way, it's possible to figure out the fix of R and S as well. The diagonals need a little bit work. Obviously, each diagonal entry will have its own coloring. So we need to count off diagonal. So there are 28 off diagonal members, and then you add the 8 diagonal members to that, so you get 2 to the power 36. So please make sure you figure that one out. So, and that's the same as the fix of S. So my computer is pretty slow now, so I can hardly write actually. Okay, good. So now it's time to apply the Burnside lemma. So the number of orbits, essentially different colorings, is equal to 1/8 times the fix of all group members, which we already did. Let me just, okay, so number of orbits equals 1/8. So we have 2 to the 64 plus 2 to the 16 plus 2 to the 32. 2 to the 16, 2 to the 32, 2 to the 16 again, plus 2 to the 32, plus 2 to the 32, plus 2 to the 36, plus 2 to the 36. So I just wrote down the remaining terms here, so just be aware that so how many 2 to the 64? We have 1 for the E. Let me actually highlight it, I guess. So for E we have 2 to the 64. For I believe for R and S we have 2 to the 36, so that's where we get the 2 here. We have 3 group actions with 2 to the 32 different coloring patterns, namely the 180 degree rotation and the reflections across the horizontal and the vertical, and then we have 2 to the 16 different colorings as well, and that solves the problem. So we are done.